In the previous lesson, we covered the basic strategy for augmentation, the A in RAG. And since the G is covered by the LLM, we have the R to improve upon. R is for retrieval. And sometimes static retrieval is not enough. When the domain of knowledge and the number of sources we need to use are vast, we need to apply dynamic retrieval strategies. A basic dynamic retrieval strategy can be pretty straightforward. If you have a repository of documents and a search engine, you can query it and retrieve the documents you find. Even Google or a Wikipedia search can do the trick. You take the first 3 results, grab the content, convert it to Markdown, and plaster it onto your context. Done. But there's a catch. Traditional search engines use pattern matching to find results, and when an end user chats with an assistant, he expects a conversational interaction. He is not Googling. So a typical search engine will not do much good in many cases. What we need is some sort of repository of documents that we can query, and that will retrieve the documents, or the fragments, that better match the query in a semantic way. We need to search by meaning, not by pattern matching. Fortunately, the field of generative AI provides the perfect tool for that: embeddings.
One of the ideas that really blew my mind in generative AI, when I started studying generative AI, was the idea that you can have an instant retrieval of some information from a semantical point of view without having to make a lot of annotations and ontologies, nothing else. Just you provide with some content and you get related content instantly, and this is what powers models like LLMs since BERT. So this idea was really interesting to me, and I was really curious to know where did it come from. And it's a long arc of history of technology and history of ideas that start in the 1950s. But the idea is that semantics, the meaning of something, of some object, is just a position in a vector space. It's a position in space, maybe a space with a lot of dimensions. So in the 50s, all of this started in the 1950s when J.R. First started working with the idea that you can extract meaning simply from context. 2 words that are used in similar context will have a relationship. So you don't need human annotation. Just by the analysis of the text, you can get. So for instance, you can get the words nurse and doctor will sit usually in text near hospital, patient, treatment, medicine. So you don't need a dictionary. So you don't need a human putting a lot of metadata saying, no, these doctors and nurses are related because they are. No, you can just, by analyzing a big corpus of information, you can extract. So it can be extracted automatically by a machine, and you don't need an ontology for it. So in the 1970s appears the idea of turning documents and queries in vectors. So you could theoretically, and in some experiments used in search engines, the idea is that you can infer similarity from a distance or an angle between 2 points in space. 2 documents or queries have different positions, and the closer the documents are, the more related they are. In the 1990s, using a big document matrix that then they compressed into a smaller semantic space, they could connect words like car and automobile, which just because those words, car and automobile, follow different patterns in the documents. So in 2003, we see a new advance in this idea that they used in this case, instead of big matrices, they use neural networks in a neural language. And the idea is that the neural network inferred the dimensions automatically without nobody defining the features. The network simply by being trained in a lot of text learned dimensions and inferred features like plural, animal, medical, or verb on its own. The core trick is just train the model, and the model creates internal representations, and we can extract these vectors from these internal representations.
In 2013, embeddings became famous. Word2Vec from Tomas Mikolov's team at Google learned word vectors cheaply from enormous amounts of text. It came in two flavors. One predicts a word from its surrounding context, the other predicts the context from the word. And the vectors captured relationships. The famous example, king minus man plus woman lands near queen, not because the model understands monarchy, but because the statistics of language produce that geometry. A year later, in 2014, Stanford's GloVe reached the same place from the other direction, global co-occurrence counts instead of local prediction windows. Two routes, one destination, meaning as geometry. There was still a limitation. These embeddings were static. The word bank had a single vector, whether it meant a riverbank or a bank account. Then, around 2018, contextual embeddings arrived from models like Elmo, GPT, and especially BERT. By reading both the left and the right of a word, they give it a different vector depending on the sentence it sits in. That is a real shift. Embeddings stopped being word vectors and became context-sensitive meaning vectors. And today, embeddings are not only for words. We embed sentences, documents, images, audio, video, code, users, products, even nodes in a knowledge graph. This is what powers semantic search, recommendation, retrieval augmented generation, which is exactly where this lecture is heading. Clustering, deduplication, and the memory behind many AI applications. And the recipe has not changed since 2003. Take something complex, train a model on a useful task, extract the internal vector, and use distance in that space as a proxy for similarity. Now, embeddings models are a very useful tool. They receive a block of text, which can be quite long, and they produce a very long vector of numbers, an embedding. Just that. And embeddings have a remarkable characteristic. Those generated by the same model tend to have a geometrical relationship akin to the semantic relationship between the texts that produce them. To see it in action, we will use another of the sample programs in our repo. This is the Embeddings Explorer. Type a word, cat, and the model turns it into its embedding. 768 numbers, a single point in space. Every embedding comes out the same length. Add another word, and the demo measures how close the 2 points are, two ways at once. Cosine is the angle between them, higher means closer. Distance is the straight line gap, lower means closer. Cat and dog land near each other. Nobody told the model they're both animals. It learned that from text. Keep going. Blue cat, black cat, even a whole sentence. Each one becomes a point, and the table resorts, nearest first. Watch the two columns agree on the order every time. Because the vectors are all the same length, the two measures are really one geometry. Now, cow, tractor, car, and car lands closest to tractor. Meaning became distance. That's the idea behind dynamic RAG. Once meaning is geometry, finding what's relevant is just finding what's near.